Okay, this is the 21st lecture and we continue our discussion on two-port networks. As we did in the last lecture, the z parameters have 4 is a 2 by 2 matrix z11, z12, z21 and z22, and for reciprocal networks z12 is equal to z21 for reciprocal networks. And we have also seen how they are defined. Z11 and Z22 are driving point impedances at ports 1 and 2 with the other port open circuited. Z11 is driving point impedance at port 1 with port 2 open circuited, and Z12 is equal to, if I write the, it is a transfer function, I1 Z11 plus I2 Z12. So, Z12 is V1 by I2 with I1 equal to 0. So, it is a transfer function between port 2 and port 1 with port 1 opened, and Z21 is V2 by I1 with I2 equal to 0. Again port 2 is open for this, and therefore, all these 4 parameters are measured with one of the ports open circuited, and therefore, these are called open circuit parameters, sometimes called open circuit Z parameters. Okay. If Z12 is equal to Z21, if this is true, that is reciprocity holds, and if the network is 3 terminal, then a particularly simple equivalent circuit can be derived like this. Let us take the equations, defining equations. V1 equal to I1 Z11 plus I2 Z12 and V2 equal to I1 Z, I should write 2 1, we assume reciprocity, therefore, it is I1 Z12 plus I2 Z22, this is reciprocity has been assumed and is reciprocal. You see, look at the first equation, I can write this as I1 Z11 minus Z12, I subtract I1 Z12 and add I1 Z12. So, I get I1 plus I2 multiplied by Z12. Agreed? I have subtracted this I1 Z12, I have added this I1 Z12. No question? And similarly, in V2, I can write I1 plus I2 Z12, and then I must subtract I2 Z12. So, I write I2 Z22 minus Z12, all right, no harm done. But this step shows that if I have 3 impedances like this, Z11 minus Z12, then Z22 minus Z12, and a third impedance here which is exactly Z12, then this circuit, this network is a 3-port network. If n is 3-port, if n is 3 terminal, then this equivalent circuit would be a physical equivalent circuit also. Otherwise, if n is 4 terminal, then this equivalent circuit is only mathematically equivalent to the equations. This is a representation of the mathematical equations. All right. This is called the Z parameter T equivalent circuit. It looks like a T, so it is called a T equivalent circuit of any 4 terminal network. The equivalent circuit has to be within inverted commas, because it may not be physically equivalent. If the original network is 4 terminal, then it is not physically equivalent, it is only mathematically equivalent circuit. Nevertheless, this circuit, this equivalent circuit is of great help in finding out, in analyzing, analysis and synthesis of networks. As an example, let us take a T network. Okay. Let us say ZA, okay, let us take Z1, Z2 and Z3. This is port 1 and this is port 2. Okay. We are required to find out the Z parameters of this circuit. One of the ways is go back to definition. Whenever in doubt, go back to the roots. Okay. Let us apply the definition. Z11, as you know, is the driving point impedance at port 1 with port 2 opened. If this is kept open, then obviously Z11 is simply equal to Z1 plus Z3. Agreed? Okay. Similarly, you can see that Z22 would be simply equal to Z2 plus Z3. Z22 is impedance looking into this port, port 2 with port 1 opened, and therefore it is simply Z2 plus Z3, Z2 plus Z3. Agreed? Let us look at the other two parameters. This is the network Z1, Z2, Z3. To find out Z12, you recall the definition of Z12, it is V1 divided by I2 with I1 equal to 0, and therefore we keep this open and we find out V1 with a current generator I2 here. Obviously, since this is open, there is no drop in Z1, so this V1 is the same as the drop across this, and therefore this is simply equal to Z3, simply Z3. V1 divided by I2, I2 Z3 is equal to V1, so V1 by I2 is simply Z3. And by the same token, if you interchange the current generator and the response, you will get this also as equal to Z21. All right. Now, another way, this is by applying definition, another way would be to compare this network with the equivalent network. The equivalent, mathematical equivalence was Z11 minus Z12, this was Z22 minus Z12, and this was Z12. So, immediately you identify Z12 as equal to Z3, and therefore, Z11 is Z1 plus Z3, Z22 is Z2 plus Z3. All right. This is one of the uses of the equivalent circuit. It is a very simple case, so there is no problem. But suppose you have a more complicated network in which there are, let us say, k plus 2 number of nodes, more complicated network, and you cannot obtain this by inspection or by finding out the input impedance. For example, finding out input impedance is also a problem. Let me show you an example. Suppose you have a network like this. Suppose you have a network like this. Let us say R1, R2, R3, C1, C2, C3. And if you are required to find out the open circuit parameters, the Z parameters, to find out Z11, you keep this open and find out the impedance looking here. Can you calculate this out by inspection? No way. No way. You know, this is not open, there is a path here, and therefore by inspection it is impossible to find. What do you do? That is the question. How do you find Z11? The thing to do is to use node equations for analysis, and let us do it systematically. Node equations. For a complicated network in which one cannot find out the Z parameters by inspection, one uses node equations, and we look at the network like this. We have n and we have 2 ports which are available. So, to the 2 ports I connect 2 current generators I1 and I2. These are after all the independent variables I1 and I2, and we identify this as one of the nodes, we call this V1, this as one of the nodes, call this V2, and so on. Okay. Well, V1 is between this point and this point, V2 is between this point and this point, and so on. And let us say these are the external nodes. Let us say there are other nodes inside the network, we call them V3, V4 to let us say Vk. There are k plus 2 nodes. Okay. No, there are 2 outside. Okay. V3, V4, no, internal nodes are this. Okay, internal nodes are this. Now, you can write node equations, and the first 2 shall be I1, I2, there are generators, there are no other generators inside, and therefore 0 and so on, 0 equal to this. Now, I1 will be a function, in general will be a function of all the node voltages, okay, and they shall be linearly related, and therefore I can write V1 sum y11, some admittance, because it is a current, each term must be of the dimension of current, some admittance, I will explain these admittances later, plus V2 y12 plus etc. plus Vk y1k, all right. All these coefficients must be admittances. Similarly, here I get V1 y21 plus V2 y22 plus etc. plus Vk y2k. The third one, third node, there is no source there, and I write 0 equal to V1 y31 plus etc. plus Vk y3k, and the final node equation, the kth node, shall be V1 yk1 plus etc. plus Vk ykk. This is the general. We will take an example later to show how this is obtained, but in general I can write these equations. Now, in these equations the constants that occur have 2 varieties. The subscripts may be the same, subscripts may be different. If you notice, if I write the Y matrix, the matrix of coefficients, then the diagonal elements are all of the same 2 subscripts, that is of the form YII. Okay. So, and the off diagonal elements are all with different subscripts ij type. Okay. Now, YII is, if you recall how node equations are written, is simply the sum of the admittances connected to that particular node. So, it is called self admittance of node I, all right. Now, Yij, that is if I and j are different, then Yij represents the admittance connected between nodes I and j. So, whenever you write the ith node equation, Yij shall occur, the jth node equation also Yij shall occur. So, this is the mutual admittance, because it occurs, it is shared by 2 nodes, it is the mutual admittance of nodes I and j, all right. Yes.
How do we define the diagonal if k is even?
How do you define?
The diagonal.
How do you define the diagonal? Any matrix shall have a diagonal. Isn't that right? 1, 1, 2, 2, 3, 3, 4, 4. This is the diagonal. Any matrix will have a diagonal. Okay.
Sir,
Yeah.
so this is a that YII is the sum of the
admittances
connected to a node, and this is the YIJ is the admittance connected between the two nodes.
Two nodes, I
Could
and
you
J.
explain that a little bit? Second.
Oh, you see, whenever you write a node equation, let's say between I and J, suppose there is an element, let's say capital Y. Then when you write the node equation for node I, you write Vi minus Vj multiplied by Y. When you write the equation for J, you write Vj minus Vi multiplied by Y. Okay? So, Y is common to the node equations for node I as well as node J, and this is why it is called a mutual admittance. One thing that should be clear is that if this element, if the element or the combination of elements between nodes I and J, if they are bilateral elements, then obviously Yij shall be the same as Yji. Isn't that right? If it is a diode, it will not be the case. If it is bilateral, then obviously Yij shall be equal to Yji if the element consists of R, L and C. Okay? And therefore, one thing that one immediately recognizes is that if the network is reciprocal, then the off diagonal elements in corresponding positions would be identical. That is, Yij shall be equal to Yji. This also is a reflection of reciprocity. Okay. What we should now realize is that there are two kinds of elements in this matrix. One is the self admittance and the other is the mutual admittance. The mutual admittances of nodes I and J have one and only one value, provided the elements composing the admittance are bilateral. Okay. In general, therefore, I can write Yij as equal to Gij, some conductance, plus some capacitance Scij plus 1 over Slij. All right. In general, I can write it like this if RLC elements compose this. Now, if Yij, well, obviously this is a general case. Even if j equal to I, it is the same. All the admittances connected to a particular node shall be of this form. There will be a conductance, there will be a capacitance, there will be an inductance. All right. So, all I j, I may be equal to j, I may not be equal to j. Okay. But the fact that Yij equal to Yji also shows that this matrix, Y matrix, the cofactors with corresponding subscripts shall also be equal, because the cofactors are obtained by deleting a particular row and a particular column, and therefore del Ij shall be equal to del Ji. And you know how to find out del Ij. You delete the ith row and the jth column and then determine the determinant and multiply by minus 1 to the power I plus j. All right, you must not miss that. And the sign of a cofactor is extremely important. Okay. Now let's see an example. No, we have not finished the discussion. You see, what I wrote was that V1, I am sorry, I1, I2, 0, 0, 0. Now I write this set of equations in matrix form. This is equal to the Y matrix Y11 to Y1k, Y21, Y2k and Yk1, Ykk. I am not writing the intermediate values, multiplied by V1, V2, Vk. And what we want to find out, you see, our aim was to find out the z parameters. Okay. So, we must express V1 and V2. We are not interested in the other node voltages, V1 and V2 in terms of I1 and I2. And obviously, if you see, V1 is del 1 1 by del, where del is the admittance, del is the determinant of this admittance matrix multiplied by I1 plus del, what would be the subscript of this? No, I1 and this is I2. I am finding out V1 del, no, it is 2 1, second row and the first column.
So very sequence.
Pardon me?
So they are identical.
They happen to be identical. Yes, they happen to be identical. But this procedure is general. Whether they are identical or not, it doesn't matter. Okay? And so, what I get is V1 equal to del 1 1 by del I1 plus del 2 1 by del I2. Similarly, V2 can be written as del 1 2 in general by del I1 plus del 2 2 by del I2. And you can see you can see that this is Z11, this is Z12, this is Z21 and this is Z22. This is the general procedure. If it is not possible to do it by inspection or by simplification, there are simplifications which one can effect to be able to obtain the Z parameters by inspection, but that we will do later. Yes, ma'am.
So the example which you had just taken, I think the Z11 and all the parameters could be determined by inspection.
Could be determined by inspection.
It's just two T's in parallel, therefore it would be.
No, but then you have to simplify. You have to make a conversion. It's not by inspection. You have to convert the two T's into pi's, combine the two and so on. We'll come to this. It's not inspection. Inspection means you don't have to look at, you don't have to write a single line of equation. Inspection means you just write down the results. It's not true for the example that I had taken. In fact, it is not true even for a very simple example. Let's take that example now, where we shall illustrate this procedure. Okay, by taking a simple pi network. Let's say we have three admittances: YA, YC and YB. This is my network and I am required to find out the Z parameters. You notice that we do require calculation. If we keep this open, here it is possible to write down by inspection. It's not that it's very difficult, but you can see that if we keep it open, then the input admittance would be YA plus YC YB divided by YC plus YB. Okay? And similarly I can find out Z22 and so on, but it would be instructive to do it by the node analysis. Let's do that. We have a V1, well, we have a current generator I1 here. We are doing it only to illustrate the general procedure. There are many ways of finding the Z parameters of this, and I2, and what we are required to find out is V1 and V2. Let's write the two node equations. There are only two nodes for which equations have to be written, this one and this one. And you see I1 therefore is equal to, what is the self admittance of this node? Sum of all the admittances, that is YA plus YC. So YA plus YC multiplied by V1, then self mutual admittance is the admittance connected between nodes 1 and 2, and that is YC will come with a negative sign, minus YC times V2. Isn't that right? The current entering here is the current going through this plus the current going through this, and this current is V1 YA and this current is V1 minus V2 YC. That is how I get YA plus YC V1 minus YC V2. Is this point clear? No? Okay. Let us write KCL at this node. What do I get? I1 equal to V1 YA plus V1 minus V2 YC, which is exactly the same as this equation.
So what is
is the general principle?
Oh, general principle is if both of them are considered positive, V1 and V2, then the mutual admittance will come with a negative sign. That is it.
Always.
Yes. Suppose V2 was considered this as negative and this as positive, then things would have been different.
So how do we take the self admittance?
Self admittance is simply the sum of all the admittances connected here. You see, this is YA, this is YC, and this is a current generator, so the self admittance is 0. Okay, and therefore this is a simple way of writing equation: self admittance and mutual admittance.
So
If there is any confusion, go ahead and write KCL.
So for the mutual, you're going to see the direct connection between the two.
That is correct.
You cannot go wrong.
No. If you go around another node, then the purpose is not served, because you are going to make the investigate the connection between this node and all other nodes in the circuit, and therefore you must not go indirectly, you must go directly.
So then, in some cases, some nodes may not be connected to the other node.
Then the corresponding term will be absent. No current goes through that. Corresponding term shall be absent. Yes. Okay.
Well, taking the self-impedance,
Admittance.
we should take the sum of the two admittance attached to it.
2, 3, 4,
And
I
all
don't
the
know.
branches attached to the node.
all the branches attached to this node. Take the admittances of all the branches attached to the node. Yes. Okay.
In this case, YC and YB won't come in series.
No, they are not coming in series. No, they are connected like this. There is no change in connection. It is only that the mathematical equation describing it is in terms of self and mutual admittance. This is a matter of convenience. And as I said, if you are in doubt, write KCL. It's always better to go to the
For
roots.
instance, the self-inductance in this case between voltage Vi and V2,
Hmm.
that is what gives us the second term YCV2, because it's connected between those two nodes.
This is mutual then. Anything
So,
connected
but with respect to the first node,
with respect to the first node.
term that we are getting there,
Yes.
that is in fact, that is why we are taking it up to the second node, and we are relating it to the voltage V2, because it's connected between V1 and V2.
We had no alternative. This is dictated by KCL. As I said, I am writing KCL here, which is exactly the same as this. We have no choice. This is how it will come. And what I am telling you is a shortcut. That is, you don't have to write KCL every time. Just write self-admittance and mutual admittance. And the convention is that all polarities of this. There is a reference node. Obviously, the reference is here. With respect to this, all voltages are considered positive, and therefore mutual admittance will come in a negative term.
So if
Okay.
there is further branching of YC, suppose one more is being connected.
Here,
So after YC,
after YC, there is one more.
then the self-impedance at point 1 will be what?
Will not change
Will not change.
because there is a node 2 here. Self-admittance is from here to the next node, from here to the next node. Sum up all of this.
Even the mutual won't change.
Even the mutual won't change. Nothing will change. Because if you identify this as a node. But suppose, there is a question here. Suppose YA consisted of 2 admittances like this, YA1 and YA2, and this is not recognized as a node. Then you would have to take the total of this. Agree?
So and if between 1 and 2,
In between 1 and 2. There is one more.
yeah.
Then you add them. If there is YC1 and there is YC2, then the mutual YC1 plus YC2 shall figure in both self and mutual. Alright? Okay. Now we will come to further complications when you come to them. This is YC and this is YB, and this is I1, I2, this is V2 and this is V1, and our equations are I1 equal to YA plus YC times V1 minus YB V2, and the second equation similarly I2 would be, pardon me, YC, that is correct, thank you, YC V2. The second one would be mutual admittance remains the same, minus YC V1 plus YB plus YC V2. Okay, and what I am trying to do now is to find out V1 and V2. You see, V1 is del 1 1 by del. What is 1 1? First row and first column. So it is yb plus yc divided by del, whatever del is, multiplied by I1 plus again del here I2. This would be del 2 1 or del 1 2. The sign here is negative and the sign of del 1 2 itself is negative. So it is simply yc divided by del. Is that okay? Is this okay? I have applied the same procedure. I have not written the matrix. I have done some, I have omitted some steps. Similarly, you can write V2 as equal to yc by del times I1 plus, what shall you have here?
Y plus YC.
A plus yc divided by del multiplied by I2. So you immediately identify Z11, Z12, Z21 and Z22. Agree? Let me write this results. This is obtained not by inspection but by node analysis, and this was to illustrate the general procedure that you will follow in the case. Okay, Z11 is yb plus yc divided by del. Z12 equal to Z21 is equal to yc divided by del, and Z22 would be ya plus yc divided by del. Okay, this is what is the network? Let me draw the network. Network is we have a ya, we have a yc, and we have a yb. What is del? The determinant of the it is ya plus yc multiplied by yb plus yc minus yc square. So it is simply ya yb. It's a cyclic summation of products yb yc plus yc ya. All right. Suppose this network, this two-port network, is equivalent to, with a question mark, we will find the condition, is equivalent to the T network like this, 2 and 3. Can you tell me, if this is equivalent to this, can you tell me the values of the T network elements? Obviously, Z12, Z21, which is Z3, and therefore Z3, let me write in a different color. Z3 must be equal to yc by del. Alright? Z3 is yc by del, and this would be Z11 minus Z12, and therefore from this I get Z1 equal to yb by del, and third element, no other alternative but to become ya by del. And you see that in the process we have derived the conversion formula for equivalence between a pi and a t. This is a pi to t conversion. This looks like a pi and this is a t. If these two networks are to be equivalent, then the t network parameters can be obtained in terms of the pi network parameters, and these are the following. All that you need is to find out del and then elements independently, yc, yb and ya. Alright. The interesting thing to notice is that Z1 is related to yb. Z1 is related to yb, the opposite element. Z2 is related to ya. Okay? In that sense, there is a symmetry. Okay? There is a symmetry. Any question on this? We will have plenty of occasions to use this equivalence in future.
You said about some condition when it is true.
The conditions when it is true is that both of them must be three terminal. Both of them must be three terminal, not otherwise. Suppose we had another element here. No. then no way, they are not equivalent. Okay, it's only when it is exactly a pi, and it's a pi if this is a short, this is a t if this is a short, they must be equivalent. Okay, we next go to the y parameters. And in y parameters, as I have told you, the independent variables are V1 and V2, the two voltages, and the dependent variables are the currents I1 and I2. So you relate I1 to V1 and V2. Obviously, if it is a linear network, then it should be a linear combination of V1 and V2, and the coefficients are termed, I have to have the dimension of admittance, they are termed y11 and y12. Similarly, you say y21 V1 plus y22 V2. And if you look at the definition, y11 is equal to I1 by V1 with V2 equal to 0. V2 equal to 0 means short circuiting port 2, that is, you have the network this is the driving point admittance at port 1 I1 by V1 with port 2 short circuited. In a similar manner, you can show that y22 is I2 by V2 with V1 equal to 0. That means it is the driving point admittance at port 2 with port 1 short circuited. This is where you measure the driving point admittance with this short circuiting. Okay. Then the other two parameters y11 V1 plus y12 V2, I2 equal to y21 V1 plus y22 V2. Let us say y12, this is equal to I1 divided by V2 with V1 equal to 0, which means that you measure the short circuit current at port 1. V1 equal to 0 means, let us see, V1 equal to 0 means you are short circuiting this, no voltage can appear across a short circuit, and you have to find I1. Now, one of the common mistakes is that the direction of I1, which direction should we take? It should go up, this is I1, you must not change the directions of the current, and you have connected a voltage source here V2. This ratio I1 by V2 shall be y12, and similarly for y21 it is I2 by V1 with V2 equal to 0, that is, you connect a V1, this is the network, short circuit this and measure this current coming up. All right. If you notice, y11 and y22 are driving point parameters, y12 and y21 are transfer admittances. Okay, two of them are driving point and the two are transfer. In the same manner that we discussed in the case of the z parameters, if the network is reciprocal, if n is reciprocal, then y12 and y21 shall be the same. Okay. If n is reciprocal, then y12 shall be equal to y21. Let us take an example. Let us take this pi network. There is an admittance yc and there is an admittance yb here. If I apply the definition of y11, y11 is the driving point admittance with port 2 short circuited. If this is short circuited, then all that you get is YA and YC in parallel, and therefore Y11 is YA plus YC. All right, is it clear? What is Y11? Y11 is this admittance with this short circuited. If you short circuit this, obviously YB drops out of consideration. So YA comes in parallel with YC, and this is Y11. In a similar manner, you can find out Y22 as equal to YB plus YC. All right. Let us find out Y12 or Y21. Y12, for Y12 we shall connect a voltage source at port 2 YC and YA, and what shall we do? Short circuit this and measure this current I1. Okay, what do you think the current would be? You see, YB is in parallel with V2, so it becomes ineffective. V2 and this voltage is 0, this also becomes ineffective. So V2 by YC would be equal to I1. No. V2 YC. No, even that is not correct. Negative of that, and therefore Y12 shall be equal to minus YC. Is that clear? Similarly, Y21 is equal to minus YC. Let me write it down, which will lead me to a very interesting results. I have YA YC YB, and I have shown that Y11 is equal to YA plus YC, Y12 is equal to Y21 equal to minus YC, and Y22 is equal to YB plus YC. Now, if I want to replace this YA, YC, YB by the 2 port parameters, let us see what happens. What is YC? YC is minus Y12. Okay. What is YA? YA is obviously the sum of the two. So Y11 plus Y12, and YB is Y22 plus Y12. Don't you see that we have obtained an equivalent circuit for a general network, a 3-terminal equivalent circuit, again either physical or mathematical, depending on whether it is 4-terminal or 3-terminal, as the case may be. Is the point clear? A general. Now let me make a formal definition. Now, but before that, what I have derived is that a general 2-port can be represented physically or mathematically by 3 admittances like this: minus Y12, and this is Y22 plus Y12. Okay, this is what I have shown by referring to a simple example. Now let me make a formal derivation. You see, my equations were I1 equal to V1 Y11 plus V2 Y12. I can write this as V1 Y11 plus Y12. Okay. Then minus Y12 V1 minus V2. Is that okay? All right. This is I1, and I2 I can write as minus Y12 V1 minus V2 plus Y22 plus Y12 V2. Is that okay?
V2 minus V1.
No, this would be V2 minus V1. That is correct. Is it okay? All right. Because my other equation is I2 equal to Y1 to V1 plus Y1 to V1 plus Y2 to V2. What I have done is I have added Y1 to V2, I have subtracted Y1 to V2. Now don't you see that this is the same as these two equations are represented by the same as this V1, V2, this is I2 and this is I1. Okay, these node equations, I am writing node equations. So I1 equal to this node multiplied by its self at no, the current through this plus current through this. The current through this is V1 Y11 plus Y12 and the current through this is V1 minus V2 multiplied by minus Y12, and therefore this is formally established as the pi equivalent circuit of a general two port. The equivalent circuit would be a physical equivalent circuit if the general two port is 3 terminal. It is a mathematical equivalent circuit if the general two port is 4 terminal. Alright?
Excuse me, sir. Sir, here we are getting y minus 1 2 as one of the admittances.
Y
Minus 1 minus y 1 2.
That's right.
So what's the physical significance of negative impedance?
It may not be negative. You know, Y12 itself may be negative. There is no physical significance of a negative impedance is that it's negative. There are possible to, it is possible to get negative resistance, negative inductance, negative capacity, no problem. You can have. Not with coils and parallel plates, we have to use active devices. Yeah.
So this you are mentioning about this particular mathematical equivalence.
That's correct.
So what kind of calculation can we make from that mathematical equivalence?
Oh, any calculation, if you are required to find out, let's say this voltage or this voltage, no problem, or the relationship between the voltages and currents, no problem, because whatever you do with those two equations, you can do with this circuit also.
So,
This is mathematical equivalence.
so then what's the problem with the physical thing? I mean, what's lacking?
It cannot be realized in that form because that was a 4 terminal one and this is a 3 terminal.
That's
Even if all these elements are positive, it will not be physical equivalent of the previous circuit because that was a 4 terminal one, this is a 3 terminal one.
So, but we can carry all the calculations.
You can carry all the calculations. Anything that you do with these two equations, you can do with this circuit also, because this circuit represents only these two equations, mathematical equivalent. Now, if it is not possible to calculate the y parameters by inspection, then what do? You do exactly the dual of what you did with z parameters. In the case of z parameters, you wrote node equations. Here you shall write loop equations, not loop, mesh equations. And in mesh equations, the coefficients would have the dimension of impedance. That is, we shall have terms like Zij and Zii. And let me introduce these definitions, these terms, that in mesh equations, Zii is the self impedance of loop I, and by self impedance we simply mean you go round the mesh and just go on adding the impedances. This is the self impedance of mesh I, and Zij is the mutual impedance between meshes I and J, that is the impedance which is common to meshes I and J, and both of them are of the form in general Rij plus Slij plus 1 over Scij. All right. So, if you write mesh equations, the matrix that you shall get would be of the form V1, V2, these are the only two sources that you connect, all the rest are 0, would be equal to Z11, well, let me make capital Z 11 to capital Z 1k, Z21 to capital Z 2k, and so on, ZK1 up to ZKK multiplied by I1, I2 to Ik. This will be the type of equations, set of equations that you get. And whatever we have said about the Y matrix, the admittance matrix, nodal admittance matrix, also holds about the mesh impedance matrix. In other words, the self impedances occur along the diagonal, and all off diagonal entries are mutual impedances. They are equal, Zij equal to Zji, if the network consists of only bilateral elements, that is if the network is reciprocal, and therefore del Ij shall also be equal to del Ji, where this del now refers to the determinant of the impedance matrix.
So won't it be always equal? Del Ij will be always equal to
Not necessarily. If you have a non-reciprocal, if you have a non-unilateral element, then no, it's not true, because current cannot flow equally well
So, but
in
by
both
taking
directions.
del Ij, we are just eliminating the ith and jth.
Yeah, but if these elements are not equal, Z21 is not equal to Z12, then obviously they will not be equal. Okay, finally what we do is we find out this currents I1 and I2. I1 would be del 11 by del multiplied by V1 plus del 21 by del multiplied by V2, from which you identify Y1 and Y2. I think this is a good point to stop. We will continue this on the Tuesday. Tomorrow we shall be doing problem sets.